Hello everybody, this is Jeff Janess and welcome to our wildlife lab using kernel densities to determine the home range of a species. In the last lab exercise we looked at minimum convex polygons, and these kernel densities we're going to look at now, they function in a very different way. Now, unlike minimum convex polygons, kernel densities can tell you what regions of the landscape an animal actually prefers. You can score every part of the landscape on how much time the animal spends there, and you can exclude areas inside the general range of the animal if the animal never actually goes there. Kernel densities do have some downsides though, and one is that it depends on parameters that are hard to estimate. In this lab example, we're going to set one parameter called bandwidth to be a particular value, but in real life the correct value is hard to guess, and the lab document provides illustrations of what our analysis would look like if we tried different bandwidth values, and you really should look those over and understand how important that bandwidth parameter can be. And kernel density analysis, when used for determining home ranges, also requires some subjective choices regarding what density value to use as a threshold for determining whether the landscape should be identified as home range or not. It's another value that's difficult to estimate. Unfortunately, ArcGIS Pro doesn't offer any method to statistically transform the kernel density raster into a probability surface. In other words, we can't use common probability thresholds like excluding the outermost 5% of the regions used. If this is a strategy you'd like to use, you'll really have to learn to code. Now, kernel density surfaces are often called heat maps in general conversation, and in fact, it's often a good idea to use this name when talking to the general public. Now, in this lab, we're going to try the kernel density tool, and we're also going to learn the tool to create contour lines. We're going to learn a logical operator tool that reclassifies the raster into true and false values, and we're going to try a tool for converting rasters to polygon feature classes. For your homework, you'll calculate the area of the general home range of this owl, and you'll also calculate the area of the region most often used by the owl, and which we assume is therefore the area most important to the owl. We call this region the core area. And unless you've been told differently, you'll also calculate one more region, which will be your choice of these four here. Either you'll calculate the area used by the owl in the daytime, or the nighttime, or during breeding season, or outside the breeding season. This is similar to the minimum convex polygon analysis, but you only have to do one of those four. And all of these values will depend on a particular density threshold value, the meaning of which should become clear as we work through the lab exercise. Now, you can use whatever density threshold you like, but you'll need to tell me what it is in these boxes so I can use the same threshold when I check your work. All right, let's get started. Now, in this lab exercise, we're only going to go through the OWL 6 locations. If you'd like to try these same methods on the OWL 83 points, then please feel free. It's just always good to get more exercise at this process. The images at the end of the lab document will show you what types of regions you should expect from the OWL 83 analysis, so you can check your work there. But we're just going to do OWL 6 in this lab exercise demonstration here. So first off, we have to load up the data. I've already got the OWL 6 points here. I've also got the backgrounds, I got the imagery, and I got a topo map. Either one might be interesting to me as I work. And before we get started, this is actually an important thing to point out here. And the kernel density function will generate a density surface based on all the points if no points are selected, and it will do it on the selected points if you do have any selected. That's probably no surprise. But this means that when you want to do an analysis on, say, the breeding season or the non-breeding season or the daytime or the nighttime locations, you have to select those points first before you do anything else. So there's going to be several steps in this analysis. We're going to create a density surface. We're going to calculate contour lines on it. We're going to identify a contour level that means something to us. We're going to use a tool to extract the portion of the density that is greater than that contour, and then we're going to convert that to a polygon. Well, all of those steps have to be done after you select the points. So the steps we go through will have to be repeated. Just be aware of that. All right, so we've got our points and everything ready to go. Okay, so let's go fire up the kernel density tool. It's here in the tools. It is in the spatial analyst tools in the density toolbox. Here it is. You could also just type it. Okay, we're going to be doing a density surface on the owl 6 points. The population field we're going to leave as none. The population field allows us to weight the points. Maybe if some points are a lot more important than other points, we could make them more important in the density analysis. And in this case, the no point is more important than any other, so we're just going to leave the population field as none. The output raster, I'm going to name it in a way that tells me what is in that data. KPD for kernel point density based on owl number 6 using a 500 meter bandwidth using all points. The output cell size, I'm going to make 5 meters. This is the resolution of the new raster. I just want it to be a little more precise. Search radius, this is what we mean by bandwidth. We're going to use a value of 500 meters for our search radius. This means it's going to look out 500 meters from every point and identify the density of points within that area. Now, search radius is probably the hardest parameter to estimate for kernel density. It's just real hard to know what's the right value to use. Now, theoretically, you'd pick some search distance that you knew actually mattered to the animal you're looking at. Maybe its perceptual range or how far it tends to move in a certain time period. But we don't always know these values as well as we wish we did. There's probably also a lot of variation from animal to animal. Usually we just have to guess. Right now I'm guessing 500 meters. And by the way, just a quick side note here, we're entering a specific bandwidth of 500 meters, but if we don't enter any value, then ArcGIS will come up with an estimated value that it thinks is appropriate for your data. And I explain how they come up with this number in the Wildlife Lab document. You see it here in the video. It's based on how generally clustered the points are to start with. So if you take your whole batch of points and find the centroid of them all, or the center of gravity of all those points, then you calculate the average distance from each point to that centroid. Well, it uses that as a basis for an estimated bandwidth. And it's a nice little equation here, but really, you got to remember that this equation has nothing to do with what you're actually measuring. It's just based on the spatial distribution of points. That may not be interesting to you at all. If you're interested in the movement behaviors of a particular animal, then this particular value may have nothing to do with what the species itself does. So you can use the default value if you want, but just be aware that it may not reflect anything important to what you're really studying. Okay, enough with that. Let's get back to the lab. We're going to calculate density in square kilometers, and it will be densities. So if you look at a value of a cell, it'll be a numeric value that says how many points per square kilometer at that location. And we'll use geodesic methods because that's just more accurate. And no input barrier features. Okay, now if we ran the tool right now, it would give us a nice density surface. But there's actually a problem. It'll give us a density surface that is limited to the rectangular extent containing these points. And we actually want to reach out a little further than that. I'm going to show you the problems with that in just a second, but let's do it accurately first. We have to set a processing extent environment, and this should be familiar from your geoprocessing lecture. Hit environment. We're going to set a processing extent right here, and we're going to use the extent of the imagery in the background. So either the topo background or the image. Either one is fine. In fact, that's why I actually supplied those data, so that you would have a method to set this processing extent. Okay, just pick that. Hit run. And there we got our kernel density surface. Now, for some reason, the people who programmed this tool made it produce a layer that is really badly symbolized. I have no idea why they chose to symbolize it this way. It almost looks like there's nothing outside here, right? But that's just not true. So first thing we're going to do is re-symbolize this in a way that makes more sense. Go to symbology. Instead of a classify method, we're going to use the stretch method. This will stretch it over all of the values. We're going to set a mask to tell it not to show us the cases that have zero density. So check that, and it makes it no color. And then you can pick any color scheme you like. I just have a few that are kind of fun for me. So I like this one. I'm going to use that as a color scheme for this. I'll just do minimum and maximum. Okay. And also I kind of like to see the landscape underneath, so I can do that by hitting raster layer and setting the transparency. I'm just going to make it to 30%. Alright. Okay, now we have a density surface. I'm going to zoom to the extent of that. Now, before we go on, I want to show you what would have happened if we hadn't set that analysis extent environment. So let's run that tool again. Here it is, Kernel Density. Pop in the owl 6 points. Set it up the same way we had it before. 500 meter search radius, geodesic. I'm not going to the environment. Just hit go. Change the symbology to something that's useful. Stretch. And set the mask to hide the zero density. Okay, notice how this density raster is clipped off at the edges. It just goes to the rectangular extent that contains all the points. But we need this outer region here. See, that's all important. That's why we set the processing extent environment. Okay, I'm going to get rid of that. All right, so now we have a density surface or a heat map. So next step is to calculate contour lines on this. And the reason we're going to calculate contours is we want to, our strategy here is to identify the highest use areas of this region. The contour lines help us see the levels of density. So the contours are just a guide to us. So we go to the tools. Contour lines are in the Spatial Analyst tools. Down in the surface toolbox, here it is. The raster we're generating contours over is our density surface. I'm going to name my output contour polyline feature class with this name. I want contours every 5 units. These are actually units of density. Remember that this raster goes from 0 to 136. That means it goes from 0 points per square kilometer up to 136 points per square kilometer. If I want a contour interval of 5, that means I'll have a line for every 5 units of points per square kilometer. All right, the base is 0. That's where we started at. Z factor is just a multiplication factor. We don't need that. Contour type. The contour that we have chosen makes contour lines. If you ever wanted to, you could make contour polygons or contour kind of slices. That's what the shells are. But we just need the polylines themselves. And we'll just ignore this maximum vertices per feature. Okay, hit and go. Generates our contour lines. There they are. Just going to make them a little lighter. Okay. Now we use these contour lines as a guide. We want to look into our map. Where would we consider a good home range to be? These contour lines give us an estimate of what the polygons would look like if we picked different density levels. If we picked everything that had a density level greater than 0, that would be this outermost polyline right here. And our home range surface would be the entire region enclosed by that outermost line. And that may be a reasonable choice. It may not. It's kind of up to you what your thoughts are about the animal, how endangered the animal might be. You know, if this is a very threatened species, we might want to go with that outermost line just because it captures the most area, and we can be confident that we'll always have captured everywhere the animal uses. But if this is a common and adaptable animal, maybe if this is a coyote or something, then we may not have to preserve the outermost region. We might want to pick an inner region. You know, maybe this line right here, we're looking at that and we think, yeah, that might be a decent home range. I'll just use that one. Well, we have to figure out what contour level, what density level that line corresponds to. So we can go to the map, hit the Explore tool, just click on that line. It looks like that is a contour level of 10. So if we wanted to capture everything inside that line, we would just go with a density level of 10 or more. If we just wanted to really capture even smaller area, that's a contour level of 35. So everywhere inside this polygon has a density of 35 or greater points per square kilometer. Now in this example, I'm just picking a density level of 5. That would be this line here. And it actually gets more than just that single line. A density level of 5 also includes this line here and this outer line here. So it gets a few little islands as well, but that's okay. So I'm going to use, for this lab, just as an example, I'm going to use a contour level of 5 and say that's what constitutes the home range of this animal. So, next tool then is to extract that portion of the raster, the density raster, that has a density greater than or equal to 5. That we're going to use a tool called the greater than or equal. This one is also in Spatial Analyst. It's in the Math and Logical toolbox, and the greater than or equal. Okay, the raster we're going to analyze is this. We're going to calculate greater than or equal to a value of 5, so we just type that number in there. And I'm going to name this the KPD kernel point density. The KPD, the kernel point density for owl number 6 using a 500 meter radius, using all points, and I'm going to call this the home range. This is going to produce a raster that has 1s and 0s. If it has a 0 in the cell, then that means it's less than 5 points per square kilometer. If it has a value of 1, that means it's greater than or equal to 5 points per square kilometer. Okay, we hit go, and there we got it. We have a raster of 1s and 0s. I'm going to turn off some of this. So, purple is 1, green is 0, so everything that's green is less than or equal to 5 points per square kilometer. Purple, greater than or equal. All right, so we are closing in. Now we want to calculate the area of this region that is greater than or equal. And so in this lab exercise, we're going to do that by converting this region to a polygon feature class, and then just calculate the area of the polygon the same way you did with the minimum convex polygon tool. All right, so that tool is called the raster to polygon tool. It is in the conversion tools from raster to polygon right here. The raster we're going to convert is this one. This tool, by the way, it only works on integer rasters. The fact that this is just a bunch of 1s and 0s means that the raster to polygon tool can work. If we try to do it on the kernel density one, probably every cell in that raster has a different value because it goes off into the decimal places. And in that scenario, this raster to polygon, it'd be trying to make a polygon feature class with a polygon for every cell, and it may not even allow us to try it. All right, so let's get a name for our new polygon feature class. I'm going to call it home range polygon for owl number 6 using the 500 meter bandwidth using all points. I'm going to choose to simplify the polygons. This is up to you. This is what the consequences of that are. If you simplify it, then the polygon will kind of follow roughly the edge, but it won't follow it exactly. If you don't simplify it, then the polygon will have this stair-step pattern to make sure it corresponds exactly with the edge boundaries. If you choose not to simplify the polygons, you get a more accurate polygon out of it, but they're usually much, much larger and slower to work with because they have so many more vertices. Yeah, it's up to you, whatever you feel is most appropriate for your analysis. All right, hit run, and now we have polygon features. Turn these off. We can use the Explorer tool to just click on it. We see what gets selected. Yeah. So now it's just a normal polygon feature class. I'm going to change the symbology because I kind of like to just see that portion that's inside. So I'm going to make the outermost polygon invisible. So just go to symbology. going to do it as unique values. When you use this raster to polygon tool, it always adds an attribute field called grid code. This tells you what the raster cell values were. So we're going to use the grid code attribute field. We have ones and zeros. Just get rid of that show all values. And I'm not going to show 0 at all. I'm just going to select that, remove, and now it's only showing the areas that met our criteria. And let's just make it a little transparent so we can see through it. Let's zoom to the extent of that. All right, so now we want to know the area of this polygon, the pink portion. Let's open up the attribute table. Here's that grid code value. You notice that there's 5 ones and 1 0. The 0 is the outermost, the non-polygon. So that's we're not going to want to calculate areas on that, but we will want these 5. See, these 5 are the 5 islands that meet our criteria. Okay, let's add an acres attribute field. Okay, and we can use the selection or not, but I'm going to calculate geometry here. It's going to be area geodesic in survey acres. Okay, these are the acreages of all those polygons. Now I want to calculate the sum of the grid code 1. Just right click on it, go to statistics. And here we are. These are the statistics on the selected features, so we care about the sum. So there are 3,184 acres that meet our home range criteria. So that has been answered. Now, next step is to figure out the core area. So let's come back to our original density. Let's look at our contour lines. Remember, the core area is that area that the animal seems to really focus on. It's most important to the animal. Well, I'm looking here and I can see that the density is obviously much higher right in here and some over here. So it's up to me to pick a threshold that captures what I consider to be the core area. So let's take a look at some options here. Maybe what is this contour? Because that looks like it really captures the highest region. That's a contour level of 60. That's what I'm going to go with. Now remember, this is a subjective choice here. Just because I pick 60 doesn't mean that's the one and only golden rule to use. It's up to you using your professional judgment to choose a value that you think is appropriate. So please, feel free to pick any other value you like. So we picked a level, so we go back to the greater than or equal tool, our kernel density, but this time we're going to do greater than or equal to a value of 60. I'm going to call it KPD for owl number 6 using a 500 meter radius, using a level of 60 for the core area. Okay, let's turn off some stuff here. So these are the areas that meet our density threshold. Now we're going to convert that to polygons. Conversion tools, raster to polygon. We're going to call this one core for polygon for owl 6, using 500 meter radius, using all the points. Okay, so now we're down to our polygons. Just to keep up our symbology that we were doing before, let's just not show that non-area. Based on grid code, we're going to remove the zeros. We're going to remove the all other values. Okay. So these are the areas we're calling the core area for our spotted owl. So how many acres have we captured there? Open up the attribute table. We're going to add an acres field. It's going to be a double precision field. Come back here. Remember that these are the two we care about. Let's just go ahead and calculate geometry for all of these. Going to be area geodesic using US Survey acres. Hit OK. Now we want statistics on these two because they're the ones that are inside. Calculate statistics. And the sum is right down here under the selection column. All right, so we've got two values now for our table. First one was 3,184 acres using a density threshold of 5. In the core area, using a density threshold of 60, was what I just showed you, except I had it hidden in the video because I didn't want you to just take that value and write it right into the homework. Just want to make sure you get a chance to do this for yourself. So notice we had to identify what threshold we used. Now the last step is to calculate the area used by the owl at some particular time of interest, like daytime or nighttime or breeding season or non-breeding. Let's just try it with the daytime points. So first off, we have to open the attribute table and select those points that were done in the day. So it'll be a select by attributes where period is equal to day. All right. Okay, we got 87 points selected. Now we're going to generate a kernel density surface over those points. So that's the tools, kernel density. Based on the owl 6 points. And it's telling us that we have the 87 daytime points selected. This should be none. Output raster, I'm going to call it KPD for owl 6 using a 500 meter radius. Daytime. Output cell size, I'm going to go with 5 again. Search radius is a 500 meter bandwidth again. Square kilometers, densities using geodesics. Now, before we hit run, remember we got to set the processing extent or otherwise we'll get a bad raster. So let's use the topo background. Now hit run. Okay, let's turn off the stuff we've had before. This is our new density surface based on just the daytime points. So let's symbolize that in a way that's more reasonable. Change it to a stretch system. Pick a pretty color ramp. Set the 0 values to be invisible. Just make it a little transparent. All right. So this is the density surface for daytime locations. Let's generate some contours over that. Here we go. Input raster is our daytime density. Output feature class, I'm going to call it, I'm going to base it on this name. But instead of all, I'm going to be daytime. Contour interval is going to be 5. Contours, hit run. Let's just make these a little brighter. Okay, so now I look at these contours and I have to make a decision. What contour level do I think would capture the daytime use? And I might go with this innermost one right here. Just one step in. That would also get a couple of islands here. So that would be a contour. That would be a density level of 5 points per square kilometer. Okay, I've made my decision. Now I need to reclassify that raster into trues and falses, whether it's above that density threshold. That's in the spatial analyst, in math, and in greater than or equal, and logical. Okay. Where the density surface is greater than 5. We're going to call this one, okay, KPD for kernel density, using AL6 at a 500 meter radius, daytime. Okay, we're making good progress. Now we just need to convert that to a polygon. Just turn off some of this. Let's go find the raster to polygon tool. Here it is. Input raster will be this one that we just made based on value. We're going to call our polygon. I'm going to base the name off of this one. Just copy and paste, saves me some typing and typos. Change all to day. Hit go. Okay. Let's open up our attribute table. Let's add an attribute field. Okay, we just right-click, go to Calculate Geometry. We're going to calculate the geodesic acreage, U.S. Survey acres. Hit OK. Now the polygons we care about are those that have a grid code value of 1. So we just right-click on it, do Statistics. And it's this number right down here under the selection column that the OWL is using in the daytime, based on a density threshold of 5 points per square kilometer. Okay, now if we wanted to redo this for the nighttime, we just select the nighttime points, or as you might expect, if we wanted to do breeding or non-breeding, we just select those points, go through all those steps again, and we get those values. Now, if you would like to try this with OWL number 83, or if you would like to try this with different bandwidths, then please feel free. You only learn more by doing it more often. If you go to the end of the document, I'll show you what kind of things you should be seeing if you try different bandwidths. This is OWL number 6 using a 250 meter bandwidth, so it's not looking out as far. You get a lot tighter circles, you might see that, a lot tighter curves. Here's the 500 meter bandwidth that we used. And if we went with a 1,000 meter bandwidth, you see how it kind of smooths everything out. This is what you get looking at all three bandwidths, just a real sense of the tightness of a small bandwidth and the flatness of a larger bandwidth. And if you keep stepping through here, you can see what I calculate for breeding and non-breeding, daytime and nighttime. And then we'll get into the same stuff for OWL number 83. So this is what I get for OWL 83. So yeah, please feel free to look through these things and see what you think. As you do the homework, think about what's good and bad about kernel density. Anything here that we did trouble you, anything you really like about kernel density. And I'm going to want to get your thoughts on a comparison between minimum convex polygon approach and kernel density, because they both have really good points, but they both have drawbacks. And I'd like you to think about those. All right. Well, thanks so much, everybody.